The production of standing waves gives us a useful way of measuring the speed of a wave without having to do distance over time measurements. If we know the frequency of the standing wave and its wavelength, we just multiply those together to get the speed of the wave. This phenomena is incredibly useful to us whenever we want to measure the speed of sound. Sound traveling in the room right now is going really fast. It would be difficult, if not impossible, for us to get a stopwatch, make a sound, time it until we hear the sound, and then do distance over time. But we can create a standing wave in open and closed tubes. Knowing the length of the tube, we can calculate the wavelength of the standing wave and multiply that by the frequency of the sound that generated the standing wave. And that's what we're going to do here. I have a 2-liter bottle with the top cut off. I put water in it, put some blue food coloring in it so you can see it better. And I'm going to put a tube in the water, and I'm going to move the tube up and down until we get the length that will make a sound wave created by one of our 3 tuning forks resonate with it. Now, you won't see this standing wave, but you'll hear it. So in order to make this a little bit easier to make the measurements, I have taped a ruler to my tube, and so when I put it in the water and lift it up and down, I can better see the distance from the top of the tube to the bottom. Now this will be a closed pipe or closed tube. It's open at the top, closed at the bottom. When we create the standing wave, we'll have a node at the bottom, the closed end, and an antinode at the top. Antinodes have large amplitudes, which means the sound will be really, really loud. And so I have to adjust the length of this closed pipe in order to make its wavelength resonate with the tuning fork that created it. So in order to actually calculate the speed of sound, we'll need to know the frequency of the tuning fork. The first one I'm going to use is 426.7 hertz. It is the musical note A, 426.7 hertz. Our tube diameter has to be known, and so for this pipe, the inside diameter is 2.9 centimeters. 2.9 centimeters, which you will need to convert to meters when you do your wavelength calculation. So I place it in there, I strike my tuning fork, and I move this up and down until I hear resonance. Right in there. So we need to know what this length is. So in order for me to see it, I'll turn it around where I can see it better. I'm going to say that's real close to 19 centimeters. We'll just call it 19.0 centimeters. So in order to calculate the resonant wavelength, you'll have to take a diameter correction, and on your lab sheet, the formula is given. You take 0.4 times that diameter, you add it to this length, and then you multiply it by 4. That's your resonant wavelength. You'll multiply that resonant wavelength by the frequency of the tuning fork, and that will give you the speed of sound in meters per second. That is our experimental speed of sound. In order to see how close that is to the accepted value, we use the air temperature correction formula. So we know that the speed of sound in dry air is approximately 331.5 meters per second plus 0.6 times the temperature in Celsius. So the temperature in the room right now is about, we'll call it 19.5 degrees Celsius. You multiply that times 0.6, add it to 331.5, and you get the accepted speed of sound in the room. You'll compare that speed of sound to the speed of sound you calculated when you multiplied the frequency times the wavelength and find your percent error. If we're really careful with this, we can normally get percent errors that are under 3%. I'm going to do the other two tuning forks, and you'll make similar calculations for them. This next one is the musical note B, and it's 480 hertz. 480. So that one looks really close to 17 centimeters. We'll call it 17.0. You'll make the same calculations with it, see what speed of sound you get when you multiply that frequency times its resonant wavelength and compare it to the temperature speed of sound. The third tuning fork I'm going to do is the musical note C. It's 512 hertz. This is not middle C, this is the one octave up, the high C, 512 hertz. Sounds like it's right in there. And this one is very close to 16 centimeters. 16 centimeters. So we'll call it 16.0. So make your calculations and let's see what we get for the speed of sound when we created a resonant wave in a closed pipe. We'll now consider resonance in an open tube. An open tube or open pipe is one in which both ends are open. In this open tube, the wavelength that resonates with it will have a node in the middle and an antinode on each end. That means from node to antinode is about 1/4 of a wavelength. From node to antinode is about 1/4 of a wavelength. So this resonant length is approximately half of the wavelength. The length of the tube is approximately half of the wavelength that resonates with it. So we'll need to double the length of the tube in order to get the resonant wavelength. Like we did with the closed tube, we'll make a diameter correction for each end in order to get a more precise wavelength. We're going to use the same three tuning forks that we used with the closed pipe, the musical notes A, B, and C. So the first tuning fork is 426.7 hertz. I will strike the tuning fork and then extend the end of the tube until we get the resonant length. We'll then measure that in order to get our resonant wavelength. Somewhere in there, but let me try it again. We'll go with that right there. So we need to know how long this tube is. So I'm going to put my ruler down, and from end to end, it's about 36.5 centimeters. 36.5 centimeters. You'll need to move the decimal and record that as a length in meters. So we now have the length, we need to do the diameter correction. Now because we have one tube that slides inside another tube, the diameter at each end is a little bit different. So I'll measure both and we'll use the average diameter in our calculation. So for this smaller end, the inside diameter is about 4.4 centimeters. The larger end, it's about 5 centimeters. So the average of 4.4 and 5 is 4.7. So we'll use 4.7 centimeters as the tube diameter. And again, you'll need to move your decimal to convert it to meters when you do your calculation. So in order to find the resonant wavelength of this open tube, we'll take 0.8, it's a 0.4 and a 0.4, one on each end. We'll take 0.8 times the average diameter, add it to this length, and then we'll double that result. that's the resonant wavelength. We'll multiply that resonant wavelength by our frequency, 426.7 hertz, and that will give us the experimental speed of sound. We will again use the air temperature speed of sound as our accepted value, and the temperature is about 19.5 degrees Celsius. So use the temperature correction for the speed of sound. That will be the accepted, and then find the percent error between your experimental and the accepted speeds of sound. We'll now do this for the musical note B. It is 480 hertz, 480. Sounds good right there. So again, I need to measure that length from end to end, and this looks like it's right at 32 centimeters, 32.0 centimeters. So you'll use that length, add in the diameter correction, multiply by 2 to get your resonant wavelength, multiply that by the 480 hertz frequency to get the experimental speed of sound. And we'll now do the 512 hertz tuning fork. It's the musical note C. That sounds pretty good. And so to measure that length, end to end, I'm getting about 30.3 centimeters. We'll call it 30.3 centimeters. So use that length in order to find the resonant wavelength, multiply it by the 512 hertz frequency to get the speed of sound for that standing sound wave. I've done the calculations for the closed pipe resonance. All three of our trials had under 5% error. One trial had under 1% error. So this is a simple but pretty effective way of measuring the speed of sound in air.